Alright, so we got our study guide, second semester exam. I'll go through momentum, energy. We'll get into waves, sound, light, talk a little bit about electricity. Each one of these videos will be a different unit of instruction. That way you can kind of go to whatever you need to go to, or do all of them if you like. So let's do a little review here on momentum. Momentum is mass times velocity. Its units are either kilogram times meter per second, or in a minute we're going to learn that it can also be a Newton times a second, but we'll see that in just a second. I'm getting into impulse, which is force times time. So force is newtons, time is seconds. And that gives you the units for impulse. The equivalent then could also be a kilogram times a meter per second. You can see how that works. Reese and Zane. You can see how that works because you have kilogram times meter per second squared, and you have a second, and they're going to cancel out, and we're going to get a kilogram times a meter per second. So you can see that a Newton times second is a kilogram times a meter per second. So both things are vectors. It's important to know. Come over here, we look at the difference between elastic and inelastic. So the first one is an example where two objects are headed to each other, they hit each other and they separate. That's called an elastic collision. The second example, the two objects are headed toward each other, they hit each other and they bounce off together. That's inelastic, like two train cars coupling together. Then our big relationship we're going to use over and over again kind of builds on this idea of impulse and momentum are almost the same thing. So impulse equals a change in momentum, which is equal to mass times velocity final minus mass times velocity initial. So that's what we're going to use in these two examples down here, which we're about ready to start. So the first example is the impulse momentum theorem. So on the impulse momentum theorem, what we have going on is we have to do something old way, new way. So both ways really involve a summation. One of the forces is given and it's 40 newtons, but there are other forces as well based on different parts of the block. I'm going to go ahead and redraw this here. So its weight is 98, which makes the normal force 98. We already know that it's being pulled with 40 on a surface that has a coefficient of 0.25. So if you take, let me grab my calculator here, hang on. Okay, I'm back. So if we take the calculator and we put in the normal force 98 and we multiply by the coefficient of friction 0.25, we come up with the friction force of 24.5. So either way you do it, old way or new way, you have to know this information. You have to know the normal force, the push, the friction, and the weight. There's not a whole lot going on in the y, so most of the action is going to be in the x. So we'll do a little, by the way, this is the old way. We're going to do a little force summation. So I'll say sum of forces in the x equals Fp minus FFk equals ma, because they're unbalanced. We get 40 minus 24.5, and that's going to be equal to 10a. So if we subtract 40 and 24.5, we end up with 64.5. Well, that's addition. So we get 15.5 equals 10a. So that makes a equal to 1.55 meters per second squared. So once we know what the acceleration is, we can then plug that into one of our magic physics formulas to figure out exactly how fast it was going when it started. That's the purpose of the problem. I don't know, I think I forgot to mention that, but that's what we want to know, is we want to know how fast it's going after a certain time period. So what we do is we use our magic physics formula number 1. So it's been a while. Good idea to review that. So magic physics formula number 1 is V equals V naught plus AT. Looks like we're after the final velocity, actually. I think when we did this in class we found the initial velocity, but this time we're going to solve for this final velocity. So I put in my initial speed, starts at rest, I would think. Looking here at my solutions I had, yeah. So it starts at rest. The acceleration is a constant 1.55, and the time that we push it for is given. If you look back up here, you can see that the time was 20 seconds that we pushed it for. So we just multiply that by 20, and that'll give me my final velocity v prime, or v, however you want to look at it. 1.55 times 20 is 31. So 31 is how we get doing it the old way. V final, sometimes we say v prime, however you want to do it. Alright, so now we will attempt to get 31 again, but this time we'll do it the new way. So we go back to our summation. You may remember that it was 40 and 24.5 in opposition. So we had the push of 40 and we had the friction of 24.5. The time that we push it for, 20, can then be used to find impulse. So impulse is force times time. So if I take these and I multiply them by their times, 20, we get some different numbers here. So we'll take 24.5 times 20. That gives me 490 for my impulse created by the friction, and 40 times 20 gives me my 800 for the impulse created by the push. If I just subtract these two things, 800 minus 490, I get 310. So that's the net impulse. The sum of the impulses equals 310. And I did that by taking the impulse to the right, subtracting the impulse to the left. That's going to be equal to not MA, but MV minus MV. So MV final is what we want to know. MV initial was 0, so we can kind of get rid of that. This is minus, by the way. But it all goes away because that's 0. So if I just put in my mass of my block, which was 10, I can divide and I get 31 this way also. So either way we do it, we still get an initial speed of 31. So just to review, V final is 31 either way we do it. The net impulse, the sum of the impulses, was 310 before we divided by 10. And the acceleration we got from the magic physics formula was 1.55. And it was positive because we were speeding up. We started at rest. Alright, so that's that one. I got one more here in Unit 7, which is the elastic collision. So in this one, we have to use conservation momentum. Basically, momentum before will be equal to momentum after, or MV plus MV. We can call one of them little v, one of them big V. We'll call this one, we'll just round that off and make that little v naught, and we'll make that big V naught. Two objects, the bigger mass I'm making with the bigger velocity, I mean, I'll make that capital M, equals little v prime plus big V prime. So we put in our masses, 1 and 10 plus 2 and 5. That's going to be equal to 1 times little v prime plus 2 times big V prime. So the total momentum before would be 10 plus 10 or 20. So 20 equals basically little v, because it's 1 times little v plus 2 big V. So we get to this part where we have unlike terms and we're stuck. Except we can use Newton's third law in combination with the conservation momentum, and we can realize that whoever's going fast at the beginning will end up going slow afterwards, and the one that's going 5 will be going more than 5. Now they don't just switch places. They would if their masses were the same, but they aren't. So what we're forced to do then is realize that little v minus big V prime, or not prime, ignore that, equals the opposite afterwards. Little v prime plus minus big V prime. So the difference before will be equal to the difference afterwards. So even though these numbers won't be the same afterwards, the difference between the arrows will be the same. So before we had 10 minus 5, so the difference was 5. So afterwards, we know the difference will be 5, but it will just switch places. So the one that was going slow will go fast, so on and so forth. So we end up with something like this. Now what we do is distribute that v, negative little v prime plus big V prime equals 5. So we want to get one of these things by themselves. The easy thing to do would be add little v prime to both sides. So 5 plus little v prime is equal to big V prime. So now I go back to my original expression that I just had a minute ago, and I sub in that for big V. So rather than saying big V, what I'll do is I'll say 2 times 5 plus little v. That equals 20. So I'm going to need a new piece of paper, I guess, to work this out. So now I want to distribute my 2 and get 10 plus 2 little v prime plus that equals 20. In other words, 3 little v prime plus 10 equals 20. So now what I want to do is I want to subtract 10 from each side. Minus 10 here, minus 10 there. I get 10 equals 3 little v. So 10 thirds equals little v. So that's 3 1/3. And so afterwards, we know that little v will be 3 1/3. So it definitely slowed down. And because we know the distance has to be 5, this makes this 8 1/3. And so it sped up. You can see that it didn't speed up nearly as much as the one with less inertia that had a drastic change. But the way we check ourselves is afterwards the momentum should be 20. So 1 times 3 1/3 is easy enough, plus 2 times 8.33, which is 19. That's basically 20, which tells me it's right. If I used fractions, it would be exact, but ain't nobody got time for that. Alright, so that's the first video for Unit 7, or for the study guide, Unit 7. And that's a little review on that. You'll see all this stuff on the exam. You just want to make sure that you know how to do those examples, because they won't be exactly the same.